Hello, my name is Tony, and this is Computer Architecture Course Reflection. Whatever we do, be it surfing the web, sending email, writing a document, is on top of computer architecture or computers. The subject explores how machines are designed, built, and operate. Knowing what inside and how it works will help you design, develop, and implement application better, faster, cheaper, more efficient, and easier to use, because I will be able to make informed decisions instead of estimating and assuming. In this course, I learned contemporary state of the art in computer hardware, including the internal working of nanoscale microprocessors to large-scale data center infrastructure and how to program many core machines as well as a cluster of visual or physical machine that power data center, which in turn enable cloud computing. In this chapter, many different classes of structure are presented, it exploiting concurrency in its own particular way. But in all cases, this broader definition of general architecture for high-performance computer emphasizes aspects of the system that contribute to achieving performance. A high-performance computer is designed to go fast, and its organization and schematic are specially devised to deliver computing speed. This chapter introduced the basic foundation of computer architecture in general and for high-performance computer system in particular. It is here, at the structural and logical level, the parallelism of operating in its many forms and size is first presented. This chapter also provides the first examination of the principal form of supercomputer architecture and the underlying concept that govern their performance. Computer architecture also represents the mean of interconnectivity for a computer's hardware component as well as the mode of data transfer and processing exhibited. Different computer architecture configurations have been developed to speed up the movement of data, allowing for increased data processing. In the end of this course, I am able to express internal structure of a computer system and the relationship between its functionalities and hardware. I also be able to analyze computer system based on different requirements and needs, and also I can solve computer related problems with computer architecture knowledge. In this course, I learn all aspects of design and organization of the central processing unit, memory, input-output, which is I/O, subsystem and their incorporation into a computer system, while the computer architecture component of the computer architecture course mainly deals with the programmer's abstract view of the machine. The computer organization component of the subject matter deals with the practical view with regards to the implementation of computer system in detail. In Learning Unit 1, which is Introduction to Computer Architecture, we discussed some of the advances in technology that led to the development of modern computer. We begin our study with a look at the different components of a computer. We then discuss the way in which we measure hardware and software performance before discussing the importance of computing power and how it motivated the switch from a single core to a multi-core processors. In order to understand computer architecture, I need to understand the components that comprise a computer and their interconnection. Set of instructions called programs describe the computation that computer carry out. The instructions are string of binary digits. When symbols are used for a binary string, the instructions are called assembly language instruction. Components interpret the instruction and send signal to other components that cause the instruction to be carried out. In Learning Unit 2, we built on our knowledge of programming to learn how to program with an assembly language. We use the instruction of a real processor, which is MIPS, to understand the basic of hardware language. We also discussed the different classes of instruction typically found in computer. We begin this unit with an overview of digital components, identifying the building block of digital logic. We will build on that foundation by writing through tables and learning about more complicated sequential digital system with memory. This unit also serves as background information for the processor design technique we learn in later units. In Learning Unit 3 and 4, we study elementary hardware components like combinational circuits and sequential circuits, functional hardware components like adders, arithmetic logical units, and databuses, and computational components like processor. This unit address the memory hierarchy of a computer and identify different types of memory and how they interact with one another. This unit look into a memory type known as cache and discuss how the main memory, which is DRAM or the dynamic random access memory, and the associated concept of virtual memory. We take a look at the common framework for memory hierarchy. This unit concludes with a review of the design of a cache hierarchy for an industrial microprocessor. In the next learning unit, we discuss the input-output devices that enable communication between computers and the outside world in some form. The reliability of these devices is important, and we accordingly discuss the related issues of dependability, availability, and reliability. We also take a look at non-volatile storage medium, such as disk and flash memory. Before learning about mechanism used to connect the computer to input-output device, this unit will conclude by discussing these system performance measure. In this next learning unit, we build upon our knowledge of computer instruction and digital logic design to discuss the role of computer arithmetic in hardware design. We also discuss the design of adders, multipliers, and dividers. We learn that there are two types of arithmetic operation performed by computer, which is the integer and floating point. Finally, we discuss floating point detail for carrying out operation with real numbers. The organization of the components making up a computer system and the semantic or meaning of the operation that guide its function. As such, the computer architecture governs the design of a family of computers and define the logical interface that is targeted by programming language and the compiler. The organization determines the mix of functional units of which the system is composed and the structure of the interconnectivity. The architecture semantic is meaning of what the system do under user direction and how the function units are controlled to work together. An important embodiment of semantic is the instruction set architecture of the system. The ISA, which is the instruction set architecture, is a logical representative encoding of the basic set of distinct operations that a computer architecture may perform and by which application programs specify the useful work to be done. At the machine level, the hardware, sometimes controlled by firmware, system directly interprets and executes a sequence or partially or the set of this basic operation. This is true for all computer courses. For those few in smallest mobile phone to potentially millions making up the world's largest supercomputer. High-performance computer architecture extend structure to a hierarchy of functional elements where the small and limited in capability or possible entire process core themselves. Modern computer technology requires an understanding of both hardware and software, since the interaction between the two offer a framework of mastering the fundamental of computing. The purpose of this course is to cultivate an understanding of modern computing technology through an in-depth study of the interface between hardware and software. In this course, I study the history of modern computing technology before learning about modern computer architecture and a number of its essential features, including instruction set, processor arithmetic, and control, the von Neumann architecture, pipelining, memory management, storage, and other input-output topics. The course will conclude with a look at the recent switch sequential processing to parallel processing by looking at the parallel computer models and their programming implication. The computer architecture class generally has a lot of hands-on exercise since I'm taking the flavor oriented towards computer science or engineering major. The focus is microprocessing. In the flavor, I get my hands on building a simple microprocessor. This gives me a bird's-eye view of how the entire microprocessing system comes together. There is also a lot of lecture component, particularly when covering architecture evolution, that occurs at a very quick pace. Therefore, I learned a few core components, which is understanding logic circuit, building architectural components from logic components, how these components permit computer operation, programming at a low level with assembly, bit level operation, and efficiency of programming. Moreover, this class provides a relaxing vibe without any pressure given. And that's all for the course reflection. Thank you.